You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Vishall Gajjar. Dr. Vishall Gajjar is a researcher working as a project scientist with the Breakthrough Listen program, a $100 million US project to search for evidence of technologically advanced and intelligent life in the universe. He received his Ph.D. from the National Centre for Radio Astrophysics in India while working with the world's largest mid-frequency radio telescope, the Giant Meterwave Radio Telescope. As one of the team members of the Breakthrough Listen team, he leads SETI activities on half a dozen radio telescopes around the globe, including telescopes located in China, Ireland, Sweden, India, Italy, and the UK.
Dr. Vishall Gajjar, welcome to the program.
Thanks for having me.
Now, Doctor, a new way of doing SETI. For all these years, we've looked for beacons, and then we moved to narrowband signals and, the hydrogen line and all of the things that are familiar to people interested in SETI. But you have a different approach, looking in a completely different area. So what differs between SETI as we've done it and SETI that as you envision doing it?
Yes. So far, most of the SETI effort has been focused on searching for this one very particular kind of signal, which we call a narrowband signal. You can imagine this as a signal that puts all of its energy in just few hertz of frequency. Now, these are great signals, and this can be used as a great beacon because so far, what we understand, we have never ever come across any signal like that in nature. And also, we don't really expect any kind of natural phenomena or natural process to produce a signal of that kind. So it's quite fitting that we like to search for kind of signal that does not typically occur in nature so that we can easily separate it out as an artificial signal. So far all the effort has gone into searching for the signal, which is great. I think that's not something that we should ignore. But my opinion was that we should try and explore other categories of signal as well, which nature also does not produce, and which are also similarly likely to be signs of artificial processes. Now, you can think about various different ways by where you can think about these different kinds of signal. One of the ways which we felt was quite interesting was pulsating signal. We do know that nature produces pulsating signal, but nature does not produce wideband, or what we call significantly not broadband. So typical pulsars do produce pulsating signal, but they produce across large range of frequency. But if you put a lot of energy into only like a few hundred or few thousand hertz, and then you repeat it every few seconds, this is again a different kind of signal that we have never come across in nature. Again, suggesting it that if we ever detect it, that is a good sign that is produced by artificial processes. And hence we went ahead and looked for these kind of signals. That was something different. And so far in the history of field of SETI, such signals have never been searched before. So we actually opened up a completely new domain or a new parameter space, which was not explored in previous SETI surveys.
So it's interesting. So it's never been looked for. So we if you get lucky and find something, we've been missing it the whole time because we simply hadn't been looking, right?
Absolutely. That's the hope. That anytime we open a new parameter space, that's always the hope that because we have been doing SETI for so many years and we haven't found any concrete evidence. And there is always this question that's lingering, that are we doing everything correct? Are we exactly looking at the right frequency? We're looking at the right kind of signal. It was not possible to do all of these things earlier because there are also computational limitation in terms of what kinds of signal we search. But now we do have those computational capabilities that allow us to search and broaden our classes of signal that we search. And hence, this is the right time to search for this signal, and that's why we did it.
Now, this is obviously with the advancements with AI, so going through and filtering the mountain of data has never been easier. So does that specifically help this to enable this now?
Absolutely. AI and ML are a great tool that we now have access to, which allow us to speed up our search, which allow us to basically look for anomalies. Although for the particular search that we are talking about today, we did not utilize any kind of ML or AI approaches, but this is just the first beginning. We would definitely be looking in the avenues of AI and ML in order to remove the false positives, because when we go ahead and do the search, we get millions of what we call hits. These are not real signal, but these are just what we call hits, in the sense they are potential signal that we need to look in carefully. As a human, we have limited capacity to kind of go through each one of them. We have limited amount of time in the day to kind of sit around in front of a computer and look through all of it. But an AI and ML can do this pretty quickly. So that's the next step that we will be deploying an AI and ML tools. We have already deployed similar tools for other classes of signal, but for this one particular class, we will also be extending the search to utilize ML and AI.
Now, give us an overview related to this of Blips.
Right. So Blips is actually an acronym, and it is one of the tools that we have locally designed utilizing this another tool called fast folding algorithm. Fast folding algorithm is a novel technique by which you can search for periodicity. Whenever you have any kind of periodic signal, you can take like a fast Fourier transform, which is a way of finding periodicity. And then you also have another way which we have utilized, is called fast folding algorithm. So far, fast folding algorithm have not been used that heavily in searches because they are quite expensive computationally. It takes a huge amount of computing resources in order to search for them. But now with the modern day CPUs, you can really do the search pretty quickly. And hence we utilize the fast folding algorithm and develop this tool called Blips. So the acronym Blips actually stands for Breakthrough Listen Investigation for Periodic Spectral Signal. It's quite mouthful, but it actually just uses the fast folding algorithm as its main kernel, and then it conducts these searches for these classes of signal where we are looking for signal which are concentrated in only like a few hundred hertz, and then they are repeating with a level of few seconds periodicity. So this is something of a new tool that we have deployed, and we are looking for a potential target to use this tool. So one of the other project that I lead is a survey of our center of our Milky Way, or the galactic center. So just to give an idea, in field of SETI, we really have no idea about potential direction where we should be conducting deep searches. Every direction are potentially useful. One can argue that, okay, maybe we should be looking at habitable planet. Maybe we should be looking at star which have Earth-like planets around it. I mean, the arguments can be never ending. But these are all depend on our definition of life. Now, our definition of life is very anthropocentric. We really have no idea about what exactly life is. So far, what we have understood is that a life can also survive in extreme conditions. So we don't necessarily need to look out for Earth-like planet inside a habitable zone. We should be looking for our other source of planet as well, all sorts of sort of different types of stars. So we, as a part of the Breakthrough Listen team, we try and be a little bit agnostic in terms of our criteria about selecting a particular stars for our survey. We try and select all different kinds of stars, and that's why we went to look at the center of the Milky Way. So if you imagine you want to do a survey, you like to kind of get the maximum return. And this survey is such that if you, so then you want to kind of come up with a direction where you're likely to encounter maximum number of stars, irrespective of what kind of star are there, whether those stars have any planets that been discovered or not. That is irrelevant. The issue is, and that is because so far what we have understood, that almost every star, even if you have found it or not, are likely to have planets around it. So it doesn't matter if you go after the star which have a planet or they don't have a planet right now. It's just our selection bias. So we want to look at a direction where you have a maximum number of stars in your line of sight. And that direction is the center of the galaxy, center of the Milky Way. So if you look towards that direction, you will encounter millions and millions of stars in just one direction itself. There are no other direction in the sky that is more likely to encounter more number of stars than that particular one. And hence, we with the Breakthrough Listen team are trying to kind of search that particular region of the sky with as much detail as possible, with as much different types of signal, with as wide frequency as possible. And hence, we kind of conducted this Blips survey towards the center of the galaxy.
Now, with the center of the galaxy and the density of stars there, if you found a candidate signal, would you necessarily even be able to tell what specific star it came from? You would just know the right direction to look for it to reacquire it, but could you ever actually work out what star it is?
So we conduct a couple of types of searches where sometimes we do targeted survey of nearby star. In those cases, it may be possible, but you're correct. In surveys like ours, where we have actually pointed our telescope towards the galactic center, and I can tell you in our survey itself, this is not actually counted, but this is based on the model of what are the typical density of stars. So we don't know how stars are distributed across the galaxy. So we can roughly estimate that if you look towards that direction, how many stars will be there in your line of sight. And we roughly calculated as close to 500,000 stars. So even if we discovered a signal, it will be very hard for us to pinpoint that it actually came from that particular star. The star may not even be visible to us. I mean, we can only see stars up to certain distances. We cannot see stars which are further out because their light kind of gets absorbed in the interstellar medium by the dust particles. We don't even know about whether they are there or not. But radio signals are special. Radio signals can travel across interstellar distances without being a little bit less disturbed. So we can detect radio signals from unknown parts of the sky where we can't even see the stars. So yes, it is not always possible that we'll be able to pinpoint a star behind any potential signal we find.
Now, are there other past data sets that could be used with this new algorithm technique to search through in a different way than what was done with the fast Fourier transform type stuff of old?
So yes, we with the Breakthrough Listen team have collected close to a few petabytes of data. And all of this data are sufficient for us to search for using the Blips pipeline. So as I said, this is just the beginning of a new tool that we just deploy. We will be deploying the same tool for other data that we have collected towards our nearest star. Now, these stars are quite close to us. So if there is any kind of transmitter on them, we have slightly better sensitivity compared to, for example, the stars that we currently consider for the galactic center. These are stars that are further out, and hence we require the transmitter, if the potential transmitter used by ETs or aliens, to be quite powerful in order for us to detect them. But the stars which are closer to us, even if they don't have powerful transmitters on them, we still have a way that we will be able to detect it. So I'm quite excited about this tool, that now we have a new way of looking at a completely new kind of signal, and we have petabytes of data that we can use on.
Now, when you're looking at the center of the galaxy in radio, are you also running up against a much, much noisier background because of the density of the stars and astrophysical phenomena that are going on there? So is it harder to actually weed through looking for clean, potentially technological signals amid all of the noise?
So in the field of SETI, astrophysical sources are not so much of a challenge for us to separate out. The bigger challenge are anthropogenic signals, so signals that are produced by our own technology. And they get seep into no matter where we look. So whether we look at the galactic center, nearby star, they are going to come on, they are going to be part of your data no matter what. So yes, there are challenges. But it's not only due to our looking at the galactic center. But you bring a really good point, which I also like to stress, that because we have a way of doing a large survey of the center of the galaxy, the same data can be utilized for other astrophysical application. So we are the same student, Akshay Suresh, which actually led this entire work, who is the first author, which I'd like to kind of give a shout out to. Akshay also led a similar work to search for pulsars. Now, pulsars are not due to ETIs, but we use the same data, exact same data, that we slightly different resolution data, but it's the same data set collected at the same time, that we search for pulsars. So galactic center itself is an exotic place, and there are a number of astrophysical sources of interest for the astronomy community that we have potential of discovering through our survey. So yes, it's a win-win, in fact.
Now, how does the Allen Telescope Array give an advantage here over a single dish radio telescope?
So any interferometer are slightly better compared to single dishes in eliminating RFI, or what we call radio frequency interference, or in just shorter term anthropogenic signals that are produced by our own technology. And the reason for that is because interferometers they have antennas that are spread across large distances, and that allows you to cross correlate signals between different antennas. And when you have a signal that is very much direction dependent, and they are all produced from some kind of a ground based transmitter, when you cross correlate signals from these antennas, you are not going to find that they are cross correlating with the highest intensity when you look towards the sky, right? Because these sources are on the ground, they are somewhere local. So that's why they are going to be potentially eliminated. And hence, telescope like ATA, Allen Telescope Array, actually helps us eliminate a large fraction of interference, which we typically get from single dishes.
When you use the telescopes, like when you're running this interferometer with however many telescope units it has, do you use them all? I mean, when you're looking at the center of the galaxy, or do you just use a selection and that gives you the data set they need, or do you turn the whole group towards them?
So I like to kind of clarify something, that in this paper, we did not use the Allen Telescope Array. We used a single dish telescope, which is the Green Bank Telescope located in West Virginia. And it's one of the largest single dish telescope, a steerable single dish telescope in the world. Now, coming to a telescope like an Allen Telescope Array or any interferometer, you are absolutely correct. Each element of the array are actually pointing towards the same position in the sky, and they are all looking at the same direction. And that's the expectation, that the signal that they are likely to receive are going to be more or less similar. And hence, you will be able to cross correlate signals from all of these different antennas and be able to kind of find out what exactly is skybound and what is produced by our own technology on the ground.
Now, you have also done work with FRBs, which are still a great mystery in radio astronomy, perhaps the greatest. On FRBs, do these data sets help you with that kind of work? Is it just not suited to catch something that transient?
It is useful. These datasets are useful to search for transient as well. So thank you for bringing that point. When we do a survey, so the same amount of data that we collected of this few tens of hours of data that we collected, we actually record in what we call raw baseband voltages. So these are the rawest raw form of the data. And during the offline process, we'll produce data for different time and frequency resolution. Because in order to search for FRBs, you need the data at extremely high time resolution and slightly poor frequency resolution. That's allowed. But in kind of searches that we do for SETI, we expect the signal to be much more narrowband. So we expect the data to be extremely high in frequency resolution, but slightly poor in time resolution. So we do this processing offline. We take the same raw data and we create multiple subset of the data with a different resolution, and then we do different signal searches. So the same data that we use here in this paper have also been searched in my older paper in 2021, where I actually conducted a search using our tool called Spandak, and we did try and look for transient signal. We did detect a couple of good transient, but they were all from a known source. So the center of the galaxy also hosts a magnetar. A magnetar is also quite bright, and they emit bright radio pulses, similar to like FRBs. So we have detected multiple, close to like a few hundred signals from this galactic center magnetar, and they are similar to FRBs. So yeah, the same data set that we have collected are useful for finding FRBs or fast transient as well.
Magnetars. Now, so is there a specific astronomical reason why the center of the galaxy would have is that density, does it hold? I mean, is there the only reason there's more pulsars and magnetars and things there is just because there's more stars in general? Or is there something about the way stellar physics works near the center of the galaxy that's conducive to making more of these above and beyond what you would find the mean rate to be within the Milky Way?
So there are hypotheses, and that hypothesis suggests that yes, the center of the Milky Way allows high rate of star formation, and plus the center of the galaxy also has a huge amount of gas to create massive stars, and massive stars create a sort of a higher amount of sort of number of supernova events, and hence you will get a large number of sort of neutron stars that are quite significantly more than the other part of the galaxy. Now, having just a population of a neutron star does not necessarily mean that all of them are magnetars. Magnetars are a very special kind of neutron star where their magnetic fields are 10 to the power 14 Gauss. So it's extremely high magnetic field. Now, this is where there are a couple of theories. I mean, we really don't know if that is true or not. We have a hypothesis that yes, there are people who have speculated that the galactic center are likely to host large number of magnetars. I mean, basically, most of the neutron star population that are residing at the center of the galaxy are indeed magnetars. While there are some other theories which suggest that magnetars may be smaller or equal, will have a similar fraction with the rest of the galaxy. We don't know which is true because we only found one magnetar so far. If there are more magnetars that are at the center of the galaxy, we'll be able to find them. There is a slight problem with magnetars. Now, magnetars are quite exotic, especially young magnetars, but they're short-lived. They don't have a lifespan long enough for us to see a large number of them, right? Because think about them. If they last for like a few thousand, few hundred thousand, or let's say, I think they last for like 10,000, 20,000 years or so. Even let's say they last for that long. So you need a lot and lots of them for you to detect them now. But let's say you have some other source. Now there are these millisecond pulsars. That is again another hypothesis that suggested that the galactic center is heavily populated with millisecond pulsars that are fast rotating with millisecond periods. Now these millisecond pulsars tend to live quite long, millions of years. So if you are ever able to find if you're ever going to look in that direction, even if the number of millisecond pulsars is not large, but just because they remain active for long duration, you have more chances of detecting millisecond pulsar than magnetar. But the fact is that since we have detected a magnetar and we have not detected a millisecond pulsar, may favor the earlier hypothesis that their galactic center might be populated with magnetar.
Now, thinking in terms, and this is the fun part about SETI, is because you sometimes have to try to think like an alien civilization. Would there be an advantage? Now, we talk about with the galaxy, the galactic habitable zone, where it's likely that life will arise, but the galactic center is usually not included in that. But it might be a good place for civilization to go if they need a lot of availability of stars and energy sources. So do you think that it's more likely that you would find advanced alien civilizations in the galaxy's central bulge as opposed to anywhere else?
So our survey don't necessarily need civilizations to exist right at the center. Now, right at the center, things are quite chaotic. You need stability for any kind of life to survive and survive long enough that you will have intelligent and you will have evolution, and then you reach to an advanced intelligent state that we have here. If you have a quite chaotic region like we have at the center of the galaxy, that might not allow such constant state of stability that you would need. But I suspect that when we look at towards the galactic center, that direction itself just gives us a large fraction of the star that we cannot expect to see any other direction. Now, just talking about the center of the galaxy, you are correct that yes, if there is indeed an intelligent life in our galaxy, what is the potential place that they are going to be interested in? And then you also ask this question, like, let's say if they try to announce their presence, if they want to kind of announce that they are there, and they want to kind of put some kind of a beacon, what are the potential places they can place such a beacon? This is what we call a game theory, that where you have two parties and we don't know each other. We have never met, but we have to come to a common conclusion. We have to come to what is something that is obvious. So this is what we call a Schelling point. A point, like you can take this example, like let's say you want to meet a stranger, have never really met the stranger, and you decide that, okay, we want to meet this at this common place and common time. What do? So you may decide to meet at the Central Station at noon. I mean, that is what we call a Schelling point. With a similar kind of idea, you can think that what are the potential places where an ETI can place a transmitter where everybody else in the galaxy would be looking. And that is, again, center of the galaxy. So if they place a powerful transmitter at the center of the galaxy, everyone else in the galaxy would be looking towards that direction sometime or the other, and they would definitely catch it. So if you really want to announce yourself, a sufficiently advanced civilization may be able to place a powerful transmitter near the center of the galaxy so that the other civilization, the rest of the galaxy, can actually know about them.
Yeah, well, look at the center of the bullseye, essentially.
Yeah.
Now, what frequencies are you looking at? Now, I know the hydrogen line is the most famous one, but are you looking at that frequency, again, as a Schelling point? Or are you looking at a broad range of frequencies all over the radio spectrum?
So our survey actually try and relax that assumption of hydrogen line. Like I mean, as you know, all previous SETI surveys, a large fraction of them focus on searching at the hydrogen line frequency. That was great, but obviously we need to expand more. So we aim to conduct the survey of the center of the galaxy starting from 1 to 100 gigahertz. So we will go in steps, because no telescope on ground has the capacity to observe such a large bandwidth at the same time. So the Green Bank telescope that we utilize a lot for the survey actually can observe from 1 to 100 gigahertz broken into multiple bands. So we started going from low band, and then we keep going to upper and higher frequency. This particular survey that we publish focus on 4 to 8 gigahertz of frequency range. But we have also collected the similar data set at lower than 4 gigahertz. And then we have also collected data higher than 8 gigahertz. So our goal is basically to survey the center of the galaxy starting from 1 to 100 gigahertz.
Now, that's an enormous amount. As the future of radio astronomy dawns, do you see it fruitful? And this has been, something that I talked with a guest on the show about before. Building a radio telescope on the far side of the moon. I mean, would that facilitate radio astronomy by just simply blocking out as much Earth interference as we possibly can?
Absolutely. I think that would be an enormous step in doing science, especially for radio astronomy, because we do have to tackle the interferences, and they are not going away. They are kind of going to increase a lot more. We have these number of satellites, Starlink satellites and other satellites, that are going to be increase in number. Even if we try and find like the most isolated place on Earth, we do have radio telescope on ground, like in South Africa and Western Australia, which are very thinly populated, and there are extremely low number of people who live in anywhere near those sites. But you cannot escape satellites. They are there. So what do? So the best solution is to go to a place where you do not get satellite interruption or do not get satellite interference, and that's the far side of the moon. And as you said, moon actually acts as a blocker of radio emission, and it can really allow you to have this radio quiet environment that you need in order to do the science that you are doing. So yes, that would be an ideal thing, to build a radio telescope on the far side of the moon. Although it's quite expensive. I mean, even taking like a 1 kilogram object in space costs you millions of dollars. Building a radio telescope on the far side of the moon is something that I don't think so is possible to do within this decade, but obviously this is something that we should all be thinking towards.
Well, with the advances in rocketry and the modern private rocket race, those costs are dropping. So yeah, eventually we might have a very quiet radio telescope sitting there on the far side of the moon that would give us probably the ultimate chance, because once you get rid of the interference, then so much more opens up. But there's also the sensitivity. I mean, if you get a really weak signal, I mean, those usually get knocked out, right? I mean, it has to be a certain strength for it to be of any interest, right?
That is absolutely true. For all our surveys, we do search beyond certain threshold, and signal needs to be bright enough for us to be detectable above the noise floor. So we expect the signal to be 6 or 7 sigma bright than the typical noise floor that we would get. But interferences are quite bright. Interferences are like 1,000 times brighter than the noise we get. So they are the most challenging one. Signals are obviously needs to be. I don't know if signals can be brought. Maybe they can be brighter than the interference. In those cases, this will be a pretty easy thing. But if they are not, then it will be very hard to read through all the interferences and get to the level of signal that may be like few times the noise floor higher, and that's where the problem comes. And that's where having telescope on the far side of the moon, where it's quiet, where everything is sitting at the noise floor. So anything that you see at even like 3 sigma or 5 sigma, it's still significant and you can look at it. So in our survey, what we have to do is just we have no other ways, but we just have to keep increasing our threshold. Like earlier, we can do maybe when you have a quiet RFI environment, you can search for signal which are at three times the noise, and that's sufficient. But now we have to keep increasing that. We have to search 20, 25 times the noise level, because most of the low level are still interferences, and they are going to create a huge amount of candidate that we can't really see by eye. So we have to keep increasing our noise level. And so having a telescope on the far side of the moon actually helps us, because it allows us to detect weak signal that we have to typically reject, just because we can't really look for signals of that level, because there are going to be millions of other signals of that level.
Now, in the history of radio astronomy, are there any signals that haunt you, such as the wow signal? Is there anything that you thought,
So I think wow signal was not something that we in the field of SETI consider it to be an extremely good example. It just got so popular, and it certainly is overhyped than it really is. We see signals like that almost every day. So these are the signals which appear for a brief moment of time and then they disappear. Now, those signals are some of the most hardest and the most challenging one that you can investigate. In our field, we require the signal to be persistent in sky, need to be bright, and need to be on for at least some amount of times that we will have time to look back at the same part of the sky, and we should still see it. Something that just disappear in like a few seconds are very hard for us to really rule out one way or the other. So wow signal is of the same or that category, and I think it definitely got over kind of it became in a popular media. It got a lot of attention, but if you talk to any real people who are working in the field of SETI, we don't consider wow signal as such a strong case. Now, coming back to your actual question about has there ever been any case like that, I don't think so. We have never really come across anything that we feel that, oh my God, this is exciting. This is actually the kind of thing we are looking for, except in the case of maybe BLC1. BLC1 was quite intriguing because we didn't really understand it at the first time when we saw it, that it was only appearing towards the direction of Proxima Cen, and when the telescope was moving away, the signal was disappearing. And again, the case was quite interesting because it lasted for like several hours. And so that's more stronger case, because typical interferences, they come and go, but they don't really track the sources in the skies, which means that if you look towards that source and you track it for a couple of hours, you consistently see a signal. That's not we have ever seen before. So that's why BLC1 was quite interesting. But obviously, when we looked at it more carefully, when we looked at the frequency where it was originating, we looked at nearby frequencies, we were able to eliminate it as interference as well.
did they ever actually pin that down to what satellite was causing the interference? Were they able to figure it out, or was it some sort of clandestine spy satellite that nobody told anybody about?
Fortunately, I don't think so. It was satellite. The reason for that satellites, especially in the low Earth orbit, they move quite fast. So they, as you know, they circle the Earth in 90 minutes. So when we look towards any direction in the sky, they don't last that long. They come and they go within our what we call a beam, because in radio astronomy we are only looking at a very, very small patch of the sky. We are not looking at the entire sky. So as long as the satellite is present in that small patch of sky, we have a sensitivity to detect it. But as when you talk about the BLC-1, which lasted for more than 2 hours, it's definitely not a satellite, because satellites cannot first of all track like as the source does. You can also argue that what about geostationary satellite? Again, the same problem. Geostationary satellites are fixed in the sky. So when you observe a part of the sky every day, they are going to be at the same part, but they don't move as the sky rotates or as the earth rotates, right? So as you track the source, like in case of BLC-1, we were continuously seeing the signal. That means the source was somewhere where it was not really dependent on where we were looking. So we suspect that this is something, the source must be in what we call side lobe. Now side lobes are quite wide and they have a quite huge area of the sky. So these are directions the telescope have sensitive, but they are they don't have a huge amount of sensitivity, but they do have sensitivity in some other directions on the ground as well. If there is a source of interference is somewhere in that direction, you may be able to pick it up from what we call as side lobes. So we have not yet really resolved what could be the source behind BLC-1, but because the frequency of BLC-1 was so similar to the interferences that we have seen before, we can rule it out.
Interesting. So a lot of this interference that you see all the time, you never really know what it was as far as what satellite, what human technology was producing.
Absolutely, yes.
Now, what about aircraft?
Yeah.
Now, how do aircraft confound it? I guess they move even more than the satellites do, don't they?
Yeah, so aircraft produce interferences at various frequencies. So we have especially between 4.2 to 4.4 gigahertz, we have some of these low flying aircraft that have these altimeter, which actually detects the ground level on aircraft, and they produce radio pulses. So we detect them. We see them as a very strange kind of a sawtooth pattern in our data. And first time when I found it, I was like, oh my God, this is aliens. Like, this is exactly what the kind of strange signal we are looking for. And like, we were looking, and then we found the same signal no matter where we look. So then I dug a little bit deeper and I found out that, yeah, there are these low flying aircraft radar signal altimeter, which produces the signal between 4.2 and 4.4, and then also produces between 4.8 to 5 gigahertz. So yeah, aircraft do also produce signals that are similar to kind of signal we search, and they do disrupt our observations.
Now, is there anything in alien civilization that really wants to tell everybody that it's there? What could it do with a radio signal to just make it look as unambiguously weird as possible? They may not be sending a message, but can you make a signal just look so strange that it blows past anything we would do with interference here?
Right. So I think the first example of kind of signal that we have historically searched in the field of SETI is a good example. Like if aliens put lots and lots of energy into like few hertz, those are the kind of signals we call beacons. They don't necessarily convey any information because they are just one frequency. They don't really have any other information embedded in them, apart from just the information that this is the direction where the signal is coming from. That's the only direction, that's the only information that that signal bears. So yeah, so this is a kind of example that signal doesn't necessarily need to be complicated. It could be the simplest of the simple form that even like a primitive technology like ours can easily detect it. You can always make signal more complicated, add any kind of artificiality, and make it something that kind of make it stand out against sources of interference or sources of like natural phenomena. But as you make it more and more complex, the chances that the other civilization might be able to detect it gets lower and lower. So in fact, your goal would be to not make your signal so complex and complicated, but to make it as simple as possible, something that is super simple, and even with this basic technology, one can easily detect it.
I see. So just a tone is all you really want to do.
Exactly.
Now, with the galactic center, with motion, all right, so red shifting and blue shifting of signals. So how bad is that with being closer? to the galactic center as opposed to looking at targets than 100 light years or something like that. So the motion of the galactic center, does that confound things more?
Certainly, if the source of signal is actually located at the galactic center, quite close to the center, then yes, their motion are going to be detectable. And we will see in what we call a Doppler drift. So signal will no longer remain stationary at one frequency, but it will basically move with time. We have tools that allow us to search for these kind of drifting signal as well. So we will be able to detect it, but we are hoping that the signal is not exactly at the center. As I said earlier, our goal is that the direction that we are looking, we are going to encounter close to 500,000 stars. This is just in the direction, and and a large fraction of these stars are not necessarily concentrated at the galactic center itself. So we don't have to worry too much about local motion. Now, yes, there are cases, for example, if the transmitter is on a planet, and if the planet is rotating around a star, what's the expected drift that you would get? So we have basically modeled all that, and when we do our search, we actually try and increase our search parameters such that we are capable of detecting things like that. So like just an example, if a transmitter is sitting on the surface of the Jupiter, like Jupiter rotates quite fast, right? So if even a transmitter is sitting on not surface, but at the extreme outer layer of Jupiter, with the rotation speed of Jupiter, you would expect certain relative velocity difference between you and the transmitter, and you would expect to see some drift. So we actually search 4 times more than that. So we actually do. So these are even larger effect than the planets rotating around a star or star rotating around a galaxy. The larger effect is if the source is kind of sitting on a surface of the planet, and if the planet is rotating, that's going to be the significant drift that we would expect to get compared to anything else. So we do keep that in mind, and we search for signals that are much more which actually encapsulate these drift that we would expect from these extreme cases.
So what's the next step with your research? What's it look like over the near term?
So we are going to expand, as I said, the search to other data set. We have a few petabytes of data that we have collected over the years as a part of the Breakthrough Listen program. And we will be applying the same tool on all of this data that we have collected, and hoping that we will be able to kind of open up a completely new parameter that we have not searched before, and going to search for something that is going to be extraordinary, that it opens up a new parameter space, opens up a new possibility in the field of SETI.
And my last question for you is, how long do you think it's going to be? If you put a time frame and estimating, we might see a signal in 20 years or something like that. What time frame might you put on that?
I like to see it in my lifetime for sure. I don't want it to be a few hundred years or so. I mean, definitely I like to see that this happen in the next decade or few decades. I think, but one doesn't know. I can only speculate. This is my anticipation. But I have a healthy kind of an argument for reason for that. And the reason is that with the tool that we now have, for example, with machine learning and AI, this was not there before. This is completely changing the game. What we were been able to do before was extremely limited. We were only able to search for these narrowband signals, right? As I said earlier. But now with the tool like with AI, we can expand the parameter space beyond our imagination, and we can look for anomalies. Like we can look for signals that we cannot even think about. We can start looking at things that we have absolutely no idea that they exist, but they are anomalous, they are strange, and they don't fit into our standard definition of signals. So a sufficiently trained, supervised or AI is able to identify anomalies. We have already tried that and demonstrated it in our previous papers, that AI can easily identify anomalies, and this is going to change the game. So I'm quite excited about that. I think this is going to be a phenomenal decade in the field of SETI. And moreover, I think the interest in this search is ever growing, With the advancement of our knowledge with the JWST, the amount of exoplanet that we are finding, this all kind of adds to the same argument that we are most likely not going to be alone. I mean, if Earth is, we have already proved that Earth is not special, right? Or there are Earth-like planets out there, and definitely we are almost there. It's just a matter of time for us to find life, and I'm quite hopeful that within the next decade or two we'll have some evidence of life.
All right, Doctor, thank you for joining us, and I wish you great luck with your work, and I hope you come back, especially if you find our good, strong candidate.
I will hope so too.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.